this video, we're going to calculate electric flux. Mathematically, the electric flux is the integral of the electric field over some surface. And then if the surface is closed, you write it like this, with this circle and the integral sign. In words, the electric flux is the amount of electric field piercing a surface. All right, so here's the setup of our problem. We have this cube, side length 2. The electric field at any given point in space is given by this expression. And you see that because it depends on y, x, and z, it's not uniform. So the field is different points in space, has different direction, different magnitude, everything. And that's going to make the flux calculation a little more involved, and we'll actually have to take the integrals. So just to kind of intuit this, let's just start by calculating the electric field at a couple different points on the surface of the box. For example, the field at the origin, 0, 0, 0, so right there. To do that, you just plug in 0, 0, 0 for x, y, and z into this expression, and you get 0 plus 0. So the field there is actually 0. So at that point, the field magnitude is 0. There's no field there. What about on the middle of this right face here? So the middle of the right face, you're 1 unit in the x direction, 2 units in the y direction, and then 1 unit in the z direction. That would put you on the middle of that right face. So that'll be 1, 2, 1. At that point, if you plug in the values, you get, so at that given point, this has a component in the j direction, in the y direction, and in the k direction, which is the z direction, which is up. So it kind of points a little that way and a little bit up, a little bit like that. All right, so the first question is asking, through which of these faces is the electric flux 0? That can happen in one of two ways. Either the field is 0 everywhere on that face, or the field is non-zero, but it points perpendicular to that face everywhere. So let's just kind of go through this one by one. And first thing I'm going to do is I'm going to label all the faces 1, 2, 3, 4, 5, and 6. 2, 3, 4. Surface 1 is on the left, so that's this surface over here. And you see that surface extends in the z direction, and it extends in the x direction. It doesn't extend in the y direction. In fact, everywhere on that surface, the y value is 0. So everywhere on that surface, the y value is 0. So let me just go ahead and write down this expression, keeping that in mind. Well, the y value is 0, so that term goes away. This will just be 4z plus 1 x squared k. I can't plug in any numbers for z and x because they vary along that surface. But what I can determine is that the electric field everywhere on that surface points only in the k direction, which is only upward. If the field always just goes upward, it's always going to be parallel to that face. If the field and the surface are parallel, there's no flux. None of the field actually goes through the surface. So we can determine that the flux on surface 1 is 0, and the reason is that the electric field is in the k direction, which is parallel to the surface. No calculation, we determine that the flux is 0. OK, surface 2. Surface 2 is a front surface. That's this guy up here. And you see that that surface extends in the y direction. It also extends in the z direction. So x is fixed on that surface. It doesn't extend in the x direction at all. X is fixed, and the value of x is 2 because there are 2 units along the x-axis. So let me just plug that into the electric field to get an expression for electric field anywhere along the front surface. OK, so in this case, the electric field has both j and k components. But of course, the j and k components, that means the y and the z directions, looks like this. So everywhere along that surface, the field is pointing somewhat in y and somewhat in z. But at no point does it point out of the box. In other words, does it point perpendicular to the surface. Those vectors are always parallel to that front surface. So again, the flux is 0. The third face is on the bottom, this face down here. Extends in the y direction, extends in the x direction. The z component down here, or the z value down here, is 0. If I plug in 0 here, you see that doesn't make this term 0. So again, you're going to have a j and a k component. That means vectors are going to extend both in the y and the z direction. So kind of something like that. But that'll get you a non-zero flux because the electric field will point into the box on that bottom surface. So in that case, because you have this k component giving you something inside, the flux is not necessarily 0. All right, now you guys can go through the other 3 faces, and using the same reasoning, you can figure out which ones are 0 and non-zero. I'm just going to put the conclusion here. So if you go through this on your own, you'll see that phi 4 is not necessarily 0 for the same reasons as phi 3. Phi 5 is 0 for the same reasons as phi 2. And then phi 6 is not necessarily 0 as well. OK, so to answer the second question of the problem, which is what is the total flux through this box, you only need to calculate the ones that are non-zero here because we just use reasoning to figure out the ones we don't need to calculate. So we're just going to add up the fluxes from phi 3, phi 4, and phi 6. OK, the first non-zero flux is flux on surface 3, which is a bottom surface. The integral of the electric field over that surface 3. What is the area element dA? The area element is always perpendicular to the surface, pointing out of the closed surface. On the bottom surface here, perpendicular pointing out would be downward. So it has a minus k component. So I'll write this as E dotted with, I'm going to write this as dA times its magnitude minus k. So this is just the magnitude of this area element, and this is its direction. I'm just disassociating its magnitude and direction. Now what is the magnitude? The magnitude, this dA just means a small, small differential area. It's like what we're going to integrate over. In this case, you can see that the bottom surface extends in y, and it extends in x. So that differential has a dy and a dx in it. And then you also have to put your limits of integration. The limits of integration are y goes from 0 to 2, and then x goes from 0 to 2. OK, and now to solve this, I'm going to go ahead and plug in my expression for the electric field into this integral. Now you'll see that the expression for electric field, it depends on y, x, and z. All right, so it depends on x, y, and z. And you're going to integrate over x and y. Well, what do I do with the z's? Well, again, on the bottom surface here, kind of when we figured out which ones were 0, we determined that on that bottom surface, z is always 0. Right? X and y, it extends in x and y, but z is 0 everywhere there. So I can go ahead and plug in z directly here. And I write that like this. I write that for this phi 3, I'm evaluating it at z equals 0, because everywhere along that surface, z equals 0. So before I plug this in, let me just put in z equals 0 here, and then write the full expression. All right, so this is the expression. We can go ahead and do the integral. You'll notice that you're going to be dotting this expression with minus k hat. When you dot j with k hat, you're going to get 0, because they're perpendicular. K hat dotted with k hat, those are unit vectors in the same direction. That'll just give you 1. So let's go ahead and simplify that. Finally, when you evaluate this expression, which I'll let you guys do on your own, you get a quantity which is minus 21.3 Newton meters squared per coulomb. So we're going to do the same type of calculation for the other two non-zero flux surfaces, which are phi 4 and phi 6. This would be a good chance for you guys to maybe pause the video, just try setting it up on your own, and then you can check back with me to make sure you're on the right track. So now we're going to take a look at the fourth surface, which is the top surface, the flux through the top surface. So phi 4 is similar to the bottom surface. We're looking at the top surface here, and you see that the top surface extends in the y direction and the x direction. The area element dA, again, that vector always points perpendicular to the surface out of the closed surface. On the top here, out of the closed surface will be upward rather than downward as it was on the bottom. So the dA is very similar to the bottom surface, except now it's a plus k hat, not a minus k hat. The dA element is dx dy again, because you're integrating over x and y. There's one more distinction between the bottom surface, which is that on the bottom surface, z was 0 everywhere. Over here, z is 0. Up here now, you're 2 units up along that axis, so here everywhere z is 2. So before you plug in e here, you want to evaluate z at 2, and then just proceed the exact same way as we did the last one. So here I've plugged in 2 for z, because everywhere on the surface, z is 2. And then just as before, when you do the dot product here, the dot of j and k hat, those two unit vectors will be 0. The dot of k and k will be plus 1. So again, just do that and proceed as before. OK, so finally, when you do this integral, which I'll let you guys do on your own, you get 64 Newton meters per coulomb for the flux through the top surface. All right, finally, we're going to do the sixth surface, which is the other non-zero flux surface. That's on the right-hand side here. So I would suggest that you guys maybe pause the video right now, try to set up the integrals for the sixth surface, and then come back and check with me. OK, so we're going to finish up with phi 6, the flux through the sixth face, which is the right-hand face. The right-hand face over here has an area element that points outward. In this case, it's to the right, which is out of the surface. That's along the y direction, so it's along the plus j direction. You're going to be integrating along x and z, so the magnitude of your area element here is dx dz. Now when you plug in your electric field here, just as before, we're going to integrate along x and z, but what do we do with the y's? Well, if you look on that surface here, everywhere along that surface, you're always over 2 units along the y direction. So here, y is always going to be 2. So I can plug in 2 for y there. And then just as before, go ahead and do the integral. All right, as before, you want to dot this expression for the electric field with your area element direction. J dot j will give you 1, j dot k will give you 0. So that'll cancel out the second term, and then you just go ahead and do the integral. When the integral is done, you get a flux of 16 Newton meters per coulomb. Adding all these up, you get a total flux through all 6 surfaces added together as 58.7 Newton meters per coulomb. Okay, so that's the end of the calculation. I just want to say one last word about the quantity flux itself. Flux is, in and of itself, not a particularly useful quantity. You're essentially just taking integrals of fields over these surfaces, and these surfaces are just imaginary surfaces in space. They don't exist. The purpose of flux is when you combine it with Gauss's law. Gauss's law uses the flux to help you find the electric field, which is the real quantity of interest. We'll discuss all that in another video, so we'll see you next time.